In this video, we shall look at few review problems associated with simple harmonic motion. First, a brief introduction. Let's assume we have a spring and we attached a block at the end of the spring. We pull the block to a certain distance and then we'll let it to oscillate. And it goes up and down about a location known as the equilibrium location. The maximum distance the block travels both above and below that equilibrium location is called the amplitude of that oscillation, which we denote as A. Let's assume the mass of the block is m and the spring is characterized by a quantity known as the spring constant K. If we are to describe the location of this block at any time t, the location can best be described by a trigonometric function. For example, the position or the location of that block at any time t can be written in a following form. Omega is a constant known as the angular frequency of this oscillation, and it can be written in terms of that spring constant and the mass of the block in a following manner. Namely, omega is the square root of k over m, and the unit for omega is radian per second. Omega is related to the usual frequency in a following manner, 2 pi f, where f is the frequency that is quantified in the units of hertz. Can we describe x in terms of cosine? The answer is yes. So which one do we use? The answer is it depends on when we start timing the oscillation. If we start timing the oscillation when the object is exactly at the equilibrium location, namely its coordinate is taken to be 0, then sine function would work, because when t is 0, x is 0. And the only way for that to happen is through the sine function. On the other hand, if we start timing the oscillation when the block is at x equals to a, then we should use the cosine function, and it would read a cosine omega t. Since at t equals to 0, x equals to a, because at t equals to 0, cosine 0 is 1. Let's for the moment stick to this function for x. What can you say about the velocity of this block at any time t? Velocity is just the time derivative of the position, so you will get a omega cosine omega t. Likewise, the acceleration of that block at any time t can be obtained by taking the time derivative of the velocity, and we will get minus a omega squared sine omega t. Now comes an important equation between a and x. By comparing the expression for the acceleration and the position, we immediately see that the acceleration can be written in terms of position in a following manner, minus omega squared x. We can get another equation that connects v to x in a following manner. From these two expressions, you see that when you take x squared plus v over omega squared, the answer is a squared. And this will enable us to express v in terms of x, namely, v becomes the square root of a squared minus x squared times plus minus omega. So these two equations, 1 and 2, would enable one to calculate the acceleration and velocity of this block, the oscillating block, at any given distance from the equilibrium location x. Now let's get to the problems. Problem 1. A block is attached to a spring with a spring constant 380 newtons per meter. At some time t, the position from the equilibrium location velocity and acceleration of the block are given to be x equals to 0.1 meter, that is the position. The velocity is minus 14 meter per second. Minus indicates the object is going upward during its oscillation. Acceleration is minus 120 meter per second squared. Find the frequency of the oscillation, the mass of the block, and the amplitude of the oscillation. So here we have a simple figure that shows the oscillation of the block. It is oscillating up and down like that. So that is the amplitude for the oscillation. So let's do part A. We are asked to determine the frequency of the oscillation. Now we are given a few things. We know the spring constant. We know the position when the velocity is minus 14 meter per second and its acceleration at that position is minus 120 meter per second squared. So we can use the equation that relates the acceleration to position, namely that since the acceleration is minus 120, frequency we don't know, and that acceleration occurs at a distance or position 0.1 meter, or the distance from the equilibrium location 0.1 meter, you see that we can determine the angular frequency as quite simply square root of 1200 radian per second, which is about 34.6 radian per second. To determine the usual frequency in the units of hertz, all we need to do is to take that angular frequency and divide that by 2 pi, which will give you 5.51 hertz. And that's the answer for part A. Now for part B, the mass of the block. We note that the angular frequency is also connected to the spring constant and the mass of the block in a following manner, square root k over m, where m is the mass of the block. So this would enable us to determine the mass. Mass equals k over omega squared. Since k is 380 Newton per meter, that is given, omega has been determined, 34.6 radian per second, and square that would give you the mass in kg. And the value is 0.317 kg. Finally, the amplitude of the oscillation. The amplitude of the oscillation can be determined from the equation that relates x to v. Do you remember what that equation is? It is the following. V equals omega square root amplitude squared minus x squared. We know the velocity is minus 14 meter per second. That's given right there. Equals the frequency has been determined. Remember, this is the angular frequency that we are referring to. And that is 34.6 square root. A is the amplitude, so a squared. X is 0.1, because when x is 0.1, v is minus 14. And you can solve for the amplitude. Doing the calculation, you will get 0.42 meter for the amplitude. And that solves the problem. Problem 2. An object is vibrating with simple harmonic motion that has an amplitude of 20 centimeters and a frequency of 4 Hz. Find the maximum magnitude of the acceleration and of the velocity, the acceleration and speed when the object's position is at x equals to 10 cm, the time required to move from the equilibrium position directly to the point 14 cm from it. So in this particular problem, we don't care which function that we are using. So we can use sine, for example, and that's going to give you x as a function of time equals the amplitude times sine 2 pi f time. So this is the angular frequency. F is the usual frequency. To find the velocity, we need to take the derivative of x with respect to time, and that's going to give you 2 pi f a cosine 2 pi f t. To proceed to the acceleration, as we have seen at the earlier of this video, we need to take the derivative of this function with respect to time, and that's going to give you minus 2 pi f squared a sine 2 pi f time. The maximum value of acceleration and velocity can be obtained simply from the constants that multiplying the cosine and sine. So the maximum value for the acceleration is given by that value, omitting the negative sign because we're interested in magnitude. So it's 2 pi f squared a. F is 4 Hertz and a is the amplitude, 20 cm, which we have to convert into meters. So if you put all these values in, you get the following: 126.3 meter per second squared. Now the magnitude, the maximum magnitude of velocity, which is, from this equation, is given by 2 pi f times the amplitude. So 2 pi, f is 4 Hertz, amplitude is 0.2 meter, and that's going to give you 5.03 meter per second. We have recorded the answers to part A there. Now part B, acceleration and speed when the object's position is 10 cm. So let's do the acceleration first. Acceleration for any position is given by minus omega squared x. So we know omega squared in terms of frequency is just 2 pi f squared x. So let's put in the numbers. Minus 2 pi, f is 4 Hertz squared, and x is 10 cm. Convert that into meter, 0.1 meter, and that's going to give you minus 63.2 meter per second squared. Now the speed is given by 2 pi f square root amplitude squared minus x squared. So f is 4 Hertz, 2 pi f is 8 pi, square root, amplitude is 20 cm, turn that into meter, 0.2 squared. X is 10 cm, so that is 0.1 meter squared, which will give you 4.35 meter per second. Again, the answers for part B are recorded here in the box. Now part C, the time required to move from the equilibrium position directly to a point 14 cm from it. So when x is 14, what is the time? That is what being asked. So substitute x equals to 14 for the x. Amplitude is 20. We don't have to convert the cm to meter here because you have cm here, cm there, so the common factor that is involved in unit conversion will just cancel out. Sine 2 pi, f is 4, and t is what we are looking for, the time when the object gets to the 14 cm mark. So this will give us the following result. Sine 8 pi t is 0.7. So let's do this calculation in degrees. So that means 8 pi radian is 180 degrees, 180 degrees. T is the time we are looking for. Arc sine, arc of 0.7 is 44.4 degrees. Solving for t, we get 0.031 second for the time. And that solves the problem. Thank you for watching.